Hello, this is an optional video on some electron configuration practice. It follows along in your book with page 13-14. So if you found that you were struggling getting through that practice on page 13 and 14, this is a place that you need to be. So we're starting on page 13, just looking at how to write our different types of electron configurations that we have for both atoms, neutral atoms like we see there with silicon and arsenic, as well as our ions that we see there with the Cl- and that Cu3+. So let's start by looking at our silicon. If we go and take a look at the periodic table, find silicon, we find that it is atomic number 14, meaning it has 14 electrons that we're going to have to account for. In accounting for those 14 electrons, silicon's 14 electrons are represented by the first 14 tiles on this table. And we need to know where on the periodic table corresponds to the different atomic orbitals within. So this very first row and these first two tiles on the periodic table represent the first energy level S block. So the first part of our silicon orbital notation and its first two electrons are in that 1s orbital. Silicon's next two electrons are in the 2s, represented by lithium and beryllium. As we continue reading the periodic table like a book, we then hit the next 6 electrons in that 2p sublevel. So we're in the second energy level, but now the p sublevel. Then we can move on to sodium and magnesium, again continuing to read our periodic table like a book. That's our third energy level, s electrons. And silicon's last two electrons are also in the third energy level, but they're in a p block. So in the orbital notation, we have to go through and represent all of these electrons. So that orbital notation of silicon, we would say where all of our electrons are. Well, we have electrons in the 1s, but we have to know how many orbitals everything has. Every s sublevel has one orbital, so we're going to represent that with one line. Well, silicon's 1s orbital is completely filled up, so we're going to put 2 electrons in it. Electrons are represented by our arrows. We have to draw one up arrow and one down arrow since they have to have opposite spins within that same orbital. So then our next sublevel that we hit is 2s. It's another s sublevel. We only have one orbital, and each one orbital can hold 2 electrons. Then for silicon, we move to that 2p section. Well, every p sublevel has 3 orbitals. When those electrons go into the orbital, it's 1 electron in each, so that's Hund's rule there, before we add the second of opposite spin, but 2p will be completely filled since we have not yet reached 14 electrons. Our next sublevel that electrons will be in is 3s. It'll also be completely filled, holding 2 electrons. And then lastly, we would end up with 3p. Well, there's only 2 electrons in 3p for silicon, but this p sublevel still has 3 orbitals that we need to draw out. Then those 2 electrons must both have the same spin, but be in different orbitals following Hund's rule, 1 in each before we go and add the second. So that would be our orbital notation. The electron configuration is then just simplifying that, where we're not actually drawing our orbitals in our arrows, rather the number of electrons in each different sublevel, in each different section that we have, is going to be represented by an exponent. So in the 1s sublevel, I'm holding 2 electrons, so we have 1s2. Then we have 2s holding 2 electrons. Our 2p holds 6 electrons. 3s is holding 2, and 3p is holding 2 as well. The noble gas notation is just going and shortening that even further. When we do that, we have to go find the noble gas before silicon. Silicon is still number 14 here. The noble gas before silicon is neon. So if we take neon's symbol and we put it in brackets, that's going to represent the first 10 electrons of silicon. And then we would just continue our electron configuration after that point, which would include our 3s and the 2 and 3p there. So again, we would put neon in brackets. That neon symbol in brackets, that's representing the first 10 electrons, that 1s2, 2s2, 2p6 part. While silicon still has 4 more electrons, 2 of which are in the 3s, and the other 2 are in that 3p. So that would be our noble gas configuration. Go ahead and take a moment and try out this next element, arsenic, on your own. Resume the video when you're ready to check that. So for arsenic, we have 33 electrons that we're going to have to account for. So let's go look at arsenic on the periodic table. So there we have arsenic number 33. For that orbital configuration, we're still starting at the very beginning of the periodic table with our 1s. We'll draw in its orbitals and electrons. Then we need to go to 2s, 2p, 3s, 3p is next, 4s, and then remember when we hit the D block, we actually go down an energy level. So this is going to be 3d, and then we go back up to 4p. So let's go jot all that down with our orbitals and electrons drawn in. We need to go through 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p to get all the way to arsenic. Every s sublevel has 1 orbital. Every p has 3 orbitals that we're going to draw in. And d sublevels have 5 orbitals. Squeeze that in there. Well, we have to fill up our lowest energy orbitals before we move on to the next. When we have orbitals available of equal energy, like in this 3p for instance, 1 electron goes in each with the same spin before we add the second. I will fill up 4s, 3d's all the way filled, so 1 in each before we add the second. And then 4p, well, arsenic is the third element in 4p, so there's only going to be 3 electrons. Each electron in 4p is going to get its own orbital. They're not going to pair up until they have to. For your electron configuration, we needed to simplify that down. Exponents are the number of electrons in that sublevel. That's also the number of tiles that we see on the periodic table in that section. Lastly, for that noble gas configuration, the noble gas before arsenic is argon. It's atomic number 18. So that accounts for the first 18 electrons of arsenic. We continue the electron configuration afterwards, 4s2, 3d10, 4p3. So let's look at our ion here, Cl-. Well, we know that when things form ions, they want to be like the noble gas for the most part. But really what's going to be important is what that charge on there means. So if we have a negative charge, that means we've gained electrons. Chlorine is atomic number 17, so it has 17 electrons. But because of that -1 charge, Cl- ion actually has 18 electrons. If it has 18 electrons, it is isoelectronic or has the same electron configuration as argon. So then we can go ahead and write out that orbital notation. And we would want to go to argon, which is sitting in that 3p6 part. So filling up our lowest energy orbitals first. There we've hit 10 electrons, and there are the last 8 to give us a total of 18 electrons. And then again, we see that's our full valence shell. So this is isoelectronic with argon, as that Cl-1 ion is. From here, the electron configuration and the noble gas configuration should be super simple. For that noble gas configuration, though, we can't just use argon. We have to still use the noble gas before. So the noble gas before would be neon, accounting for the first 10 electrons, and then we would still have the 3s2, 3p6. We need to do that to make sure that we can see what's going on that valence electron side. If I just have argon in brackets with nothing else, that doesn't tell me anything else about the electrons, but seeing that 3s2, 3p6 tells me, oh, hey, I have this full valence shell in the 3rd energy level. All right, so last one, take a look at your Cu3+. It's another ion. Go ahead and give this one a go and resume the video when you're ready to check. Well, copper 3+, copper has 29 electrons. That 3+ charge means we've lost 3 electrons, giving us 26 total electrons. However, the other thing to remember here is that those first electrons that we lose are going to be from the valence shell. So we're actually losing the 4s2 electrons first. But let's start by getting our electron configuration for just the plain old copper, not the ion. Okay, so this is our orbital notation for just copper, again, not the ion. So that has 29 electrons in it. Well, we are going copper 3+, which only has 26 electrons. But the electrons that are going to be lost first are the ones in the highest, or that valence energy level. So when we remove 3 electrons, the first 2 that we're going to remove are going to be from that 4s sublevel. Then the last one that we remove would then be from the 3d. We're going to have to remove from that valence energy level first. So then that's going to leave our orbital configuration with no 4s section and just one of the 3ds. And actually, we're not going to lose that 3d electron, my bad there. We're going to lose one of these doubled up electrons. So then we end up with only 8 electrons in that 3d section, 1 in each orbital before we add the second. So those last 2 electrons will be all single and lonely. Okay, so again, removing those 3 electrons, we need to remove the electrons from the 4s because that's the highest valence energy level. And then we removed our 3rd electron from that 3d sublevel. So when we go and write our electron configuration, it needs to match. We'd have the 1s2, 2s2, 2p6, 3s2, 3p6, 4s0. We could also leave that out, and then we need to end in that 3d8. For the noble gas configuration, we would still use the noble gas before, which in this case, before copper is argon, and then we would continue with what comes after argon, which would be the 4s, but we don't have any electrons in there, so again, we can just leave it out, and then we're left with the 3d8. So that's how that will work for our ions. Moving on to part 2, practice on page 14, we have a little more things that we need to be able to find from these electron configurations. So in part 2 here, we're looking at the electron configurations or orbitals notations that are given to us and finding the total number of electrons, valence electrons, and the element. So total number of electrons, really easy. And this first one, we're just counting our arrows. So 1, 2, 3, 4, 5, 6, 7, 8. Valence electrons are the electrons in the highest energy level. Remember, this big number up front represents our energy level. 2 is the highest energy level, so all electrons in the second energy level are valence, so that's going to be 6 of them. while our element with 8 total electrons and 6 valence electrons is oxygen. So if we go and look at this next one, we have that noble gas notation. So we have a few things. We could count up our electrons first or go to that place on the periodic table. Either way. So if we count up our electrons, neon is number 10, so that's 10 electrons. Then plus 2, that's a total of 14 electrons. Well, all of neon's electrons are in the first and second energy level, which means the third energy level is valence. So we need to count all the electrons in the third energy level. So that's 4 valence electrons that we have. 4 valence electrons and 14 total electrons is silicon. So I'm going to let you go ahead and give these other 3 a go and resume the video when you're ready to check. Okay, so looking at these, if we go to that last spot, 3D4 on the periodic table, we find that it is chromium. We can also add up all those exponents and find that we have 24 total electrons here. 2 of them are valence. Valence electrons are in the highest energy level, which is the 4th energy level here. On the next one, we can go to that 4p5 spot. Going to the 4p5 spot, we find that that is bromine. It has 35 total electrons, which we'll find if we add up. Argon's 18 plus 2 plus 10 plus 5. There are 7 valence electrons. The highest energy level is the 4th energy level, so we have 2 plus 5, 7 valence electrons. On this huge guy here, if we add up all of those exponents, we should end up with 83. Going to the 6p3 spot on the periodic table, we find that that is bismuth. For our valence electrons, our highest energy level is the 6th energy level, which has 3 plus 2 electrons there. So let's go ahead now and take a look at part 3. I'm actually going to give you a moment to try out part 3 here, and we'll resume the video when you're ready to check. So on number 1, we want 9 total electrons. Well, if I look at A, we have 1, 2, 3, 4, 5, 6, 7 electrons. We'll find the ones with 9 total, and you should have found that only B had 9 total electrons. Then we want the one with 3 valence electrons. Valence electrons, we're looking at the highest energy level, which for all of these is the 2nd energy level. The only one that only has 3 valence electrons or 3 electrons in the 2nd energy level is D. E is not 3 valence electrons. It is 5. We can't forget about these 2 S. They are also in the highest main energy level, which is that 2nd energy level. For number 3, looking for 5 total electrons. The only one with 5 total electrons is going to also be D there. The first one, we have 7. B, we had 9 total. C was 8. Here we have 5, and then 7 again in E. All right, lastly, we want to know what is represented by this Lewis dot structure in number 4. Lewis dot structures, remember, tell us the number of valence electrons. So we want something then with 7 valence electrons. Again, valence electrons are in the 2nd energy level, so this has 6 valence. That has 7. This guy has 6. This guy has 3 again. And here we have 5. So 7 valence electrons would just be B. So there you have it. Some practice on electron configuration stuff. We'll have more multiple choice that we'll be looking at in class.